For this video, I'm going to go ahead and walk through a few of the problems in the extra reviews for finals posted on Schoology. This is not by any means a complete review for the final, however, it should help you with some of the harder topics. Right, we're going to begin with factoring. This first problem that you see on the left is our difference of two squares pattern. That means that there are two terms, there happens to be subtraction in between them, and the coefficients are perfect squares, and the exponents are even. In order to factor this problem, we square root each of the terms, and then our answer will have the square roots of those terms, 6y and 5, and we are going to have two parentheses, one with a plus and one with a minus. In our next problem, we have a trinomial. Now when trinomials don't start with 1, these tend to be a little bit more challenging. One of the things we talked about was using a grouping method to factor these. With that grouping method, we look at the product of the first and last term, and in this case that would be negative 18, and the middle term, which is 7. Numbers that multiply to equal negative 18 and add to equal 7 are 9 and negative 2. So what we're going to do is we are going to rewrite that middle term, 7a, as 9a minus 2a. And it will look like this. 6a squared plus 9a minus 2a minus 3. And then now what we do is we factor the problem by grouping. My first two terms I can take out of 3a. And my last two terms, all I can do is take out a negative 1. And then what I want you to notice here is that these two parentheses are the same. So now we can pull the parentheses out as greatest common factor, giving us 3a minus 1, 2a. Here we see a perfect cubes trinomial. When factoring our perfect cubes, we talked about the SOAP acronym. With this acronym, the first sign is always the same as the given problem, the second sign is the opposite, and the third sign is always positive. If you look up top, you'll see the general factoring pattern. When we look at this perfect cube that we have here, first what we have to do is break it up into a short parenthesis and a long parenthesis. Take out our short parenthesis, we cube root both of the terms, giving us 2x and 3. Now we fill in our signs using the SOAP acronym. We use the same sign, the opposite sign, and then we are always positive. After that, the way that we get the terms in the trinomial is we square the first one, we multiply them together, and then we square the last one, giving us 4x squared, 6x, and 9. Notice that we don't pay any attention to the signs of 2x and 3. We use the SOAP acronym to take care of our signs. Also notice that when we square the 2x, we square the 2 as well. If we look at the problem on the right, this problem has 4 terms. Whenever your problem has 4 terms, then that means you want to try to use a grouping technique. And grouping is similar to what we did on our trinomial problem on the last slide. So if I look at my first two terms, I can pull out a 5x squared. And if I look at my next two terms, I can pull out a negative 9. And that gives me 5x squared minus 9 times x plus 2. Now, if this were to factor further, we would have to factor that again. In this problem, it does not, but that is something that you want to be cautious of. The next grouping of problems talks about a variety of ways that we have simplified throughout the semester. The first one addresses some of our exponent rules. One of the rules that we've talked about with exponents is that if we see a negative exponent, we need to move that term to the bottom of the problem. We've also talked about how if two terms with the same base are multiplied, then we add their powers. If they are divided, then we subtract their powers. For this next problem, what I would do is I would begin by distributing the negative 2 power. A lot of times people want to fix the negatives first, and there's nothing wrong with that. However, in this problem, after flipping the negatives, we would still have another negative. So we may as well deal with it from the beginning. Alright, so what I would do here is I would distribute this negative 2 power to all terms in my problem. And that would give me 5 to the negative 2, 8 to the 4th, b to the negative 12, over 4 to the negative 2, c to the 6th. Then at this point what I would do is I would identify every term that had a negative power, and I would move those terms to the other side of the fraction. The terms with positive powers stay put. So that would give me a 4 squared in the numerator, which we know to be 16, a to the 4th over, and then a 5 squared in the denominator, which we know to be 25, b to the 12th, c to the 6th. For the problem on the right, when we see problems of this type, we want to go ahead and factor each term first. We do not want to start just slashing things away. That is a big no-no, so please do not do that. Take a minute and factor all of these and try and cross off common factors. After factoring, I can go ahead and any factor in the numerator can cancel any factor in the denominator. I see that my x plus 6's will cancel and reduce. One of my 2x minus 3's will cancel. And I can also cancel another one of these if I recognize that they are opposites. So when these two terms cancel, they will cancel and result in a negative 1. If I rewrite everything that I am left with, what is remaining gives me a negative 1 times the quantity x plus 1 over 3 plus 2x. This next problem is similar to the one before it. However, we need to remember when we see division, we have to flip the fraction that is after the division sign. Pause the video and give this one a try. What you can see here is everything is canceled, and as I canceled, I flipped the second fraction at the same time. Once I go ahead and cross off common factors, I can see that nothing remains. Now, if everything reduces in a fraction, that is not equal to 0. It is actually equal to 1. Imagine if we had 12 over 12, and you continually reduced the fraction 12 twelfths, it wouldn't actually equal 0 when you were all done. The strategy that I taught in class for complex fractions was to find the LCD for all terms in the problem, and then multiply this LCD on all terms, even if the term was not a fraction. In this problem, our common LCD is going to be 2x plus 1. And if we multiply 2x plus 1 on every single term that we have, we will see for each term, something will cancel off of its denominator. And the end result is we no longer have a fraction of a fraction. If I multiply together what remains, in my numerator I have 3 times 2, which is 6, and in my denominator I have x plus 1 times 5 times 2, which gives me 10x plus 10. Now, I'm not allowed to reduce a single term in this problem. However, I can factor out a 10 in my denominator. And then this 10 and the 6 can reduce to a 3/5. And my final answer would be 3 over 5 quantity x plus 1. When simplifying radicals, you want to try to find pairs. If your problem is a cube root, you need 3 of a kind. Fourth root, you need 4 of a kind. In this problem here, we are adding and subtracting radicals. Therefore, I need to simplify them and make them so that they are like radicals. Like radicals means that they have the same number underneath the radical and the same index. And if that happens, then we can add their coefficients in front. If we look at this problem here, I can break down each of these. And as I break them down, any pairs that I circle come out. If there is already a number out front, then the pair that comes out multiplies with the coefficient that's already there. So on my second term, the 3 that is there multiplies with the 4 to give me 12 root 5. Now that all of these terms have the same radicand, which is this part right here, I can go ahead and add the numbers in front. 1 minus 3 is negative 2, plus 12 is positive 10 root 5. Now in the example on the right, we want to rewrite this problem with exponents. Things to remember are that this right here is our index, and our index goes in the denominator. This right here is our exponent, and the exponent goes in the numerator. So this would be rewritten as p to the 7/3, q to the 6/3. And then if we can reduce that fraction, then typically we will go ahead and do so. You're never going to write your exponents as mixed numbers. When dealing with imaginary numbers, we want to remember the powers of I. The powers of I go in a pattern, I, -1, -I1. We remembered this by the little children's chant, I won, with negatives in the middle. So if I give you something like I to the 25th, rather than walking through this pattern 4 times, we can use this simple rule over here. We can take our exponent of 25 and we can divide it by 4. And 4 goes into 25, let's see, 24, so 6 times with 1 remaining. So since I have a remainder of 1, that remainder tells me which exponent the expression is equivalent to. So this is equivalent to I to the first, which is just I. On the problem on the lower left, we are not allowed to leave an I in the denominator because an I is really a radical of -1. So I need to multiply by the conjugate, and the conjugate is going to be 5 plus I over 5 plus I. The complex conjugate is the same binomial, we just switch the sign in between the real and the imaginary terms. After we do this, we FOIL across the numerator and the denominator, and then we simplify. After FOILing, you'll see that my numerator simplifies to be 11 plus 23I, and my denominator simplifies to be 26. If all three of these front numbers, the 11, 23, and 26, were divisible by the same common factor, then we will go ahead and reduce. Since they aren't, then we are done. On the problem with the top right, we want to go ahead and distribute. After we distribute, any powers of I that are greater than 1 must be dealt with. We are not allowed to leave powers of I that are greater than 1. So this becomes 8 minus 6 times -I plus 24 times -1, and our final answer is -16 plus 16I. When dealing with work problems, we want to consider this simple equation: work equals rate times time. We have two people that are working together, and the numbers that we are given, 20 hours for Jack and 12 hours for Cheryl, represent their total job time. What we need to do is we need to find their hourly rate. So if Jack paints the entire apartment in 20 hours, then that means in 1 hour he paints 1/20th of the apartment. Cheryl requires 12 hours to do the same thing. Apparently, she is just more efficient, and that rate is 1/12. How long would it take them to work together? If they're working together, this means that their times are the same, so we can put T here and T here. Now their work is going to be the product of their rate times time. So that means that this gives me 1/20th T and 1/12th T. And I can think about this like Jack's work plus Cheryl's work adds up to equal 1 painted room. So I'm going to take the work that Jack does, 1/20th times T, and add it to the work that Cheryl does, 1/12th times T, and that is equal to 1. At this point, I find the LCD of the problem, which is 60, and I multiply both sides by 60. Don't forget to multiply on the right. That is a common mistake many people make. This leaves us with 3T plus 5T equals 60. And by dividing by 8, we find out that our final answer is 15/2 hours. In this problem, we see a person driving at different speeds covering the same distance. So we can go ahead and fill in the distance column that these distances are the same. And we're going to use the formula that distance equals rate times time. On the way from Chicago to Detroit, he averaged 50 miles an hour. Going the other way on the way back, he averaged 40 miles per hour. And his total traveling time was 36 hours. So that does not mean that we put 36 in each of the T slots. What that means is that if we put T here, then this column is going to have the rest, which would be 36 minus T. And I know that distance equals rate times time, and I know that both of these distances are the same, so I can say that the distance there equals the distance back. Therefore, I can do rate times time there equals rate times time back. And then we can go ahead and solve this simple linear equation. After solving the linear problem, we get that the total time is 16 hours. However, that was not the question that was asked of us. We were asked to find the distance between the two cities. Therefore, now we have to go back to the original problem and plug our time in. So my distance is going to be 50 times 60, which gives me 800 miles. When we are dealing with chemistry problems, what we are looking at is what happens when I mix solutions of different concentrations. The concentrations will be given as a percentage, which we have to then turn into a decimal. We do this by moving the decimal place 2 to the left. The equation that I have here is an alternative to using the chart. What you see is I have the strength of the first liquid times its quantity plus the strength of the second liquid times its quantity equals the desired strength times the total quantity we get. The reason why we have to call this our total quantity is because let's say I have this bucket and I dump some liquid in here from a 10% and I dump liquid in from the 35%. When I have done, I have dumped in liquid twice, and the total volume that is in this bucket is equal to the total quantity of liters. For this problem, I would have a strength of 0.10 times x, because I don't know how many liters I need. That's what I'm trying to solve for. Then I would have a strength of 0.35 times 2, and that is going to equal my desired strength of 0.25, and then my total quantity is going to be x plus 2. If we finish solving the problem, we see that we need 1 1/3 liters of the 10% solution. Now, some people will choose to clear all the decimals in the problem. That is fine. If you do choose to clear all of the decimals, you would need to multiply every single coefficient. That means all of these guys right here by 100 to move the decimal over 2 places for all terms. When we are dealing with variation, there are 2 formulas we need to remember. Direct is y equals kx. Inverse is y equals k divided by x. In the first problem, we see that y varies directly with x. So that means that we can start with the equation y equals kx. Next, we go ahead and we plug in these given values. We are told that y is 12 when x is 8, and I can use that to solve for my k value. By dividing by 8, I find out that k is equal to 3/2. Now I have my new equation that I can use. Y equals 3/2 x is the equation that represents the direct variation here. I'm asked to find y when x is 52, so 52 gets plugged in right here. Y equals 3/2 times 52, giving us 78. In this next problem, we are told that y varies inversely with the square root of x. That equation would be y equals k divided by square root of x. We're going to plug in the values that we are given, giving us the equation 24 equals k divided by square root 9. Square root 9 is 3, and if I multiply 24 by 3, I get 72. So now my equation is y equals 72 divided by square root x. If I plug in 225 for square root for the x, I then get 72 divided by square root 225, 72 divided by 15, which reduces to give me 24 divided by 5. When dealing with projectile problems, we will always give you the equation. In this problem, we give the equation x equals negative 16t squared plus v sub 0 times t. T equals the time in seconds that it takes an object that is going a velocity of 64 to return to ground after it has been shot up in the air. Now, the question asks how long it takes for the projectile to return to the ground. If it returns to the ground, that means that the height equals 0. So I'm going to say 0 equals negative 16t squared plus, I'm going to plug in my v sub 0 for v, 64t. This problem factors nicely, giving me negative 16t as a GCF and t minus 4 as the remaining parenthesis. If I solve both of these parentheses, I get t equals 0 and t equals 4. Obviously, the first one is when the object took off, so t equals 4 seconds is the answer that I'm looking for.